Hi, welcome to another video. This is a revised look at this ZeroPlus PC based Logic Analyzer from the LAP-C series. This one's called a Logic Cube, made in Taiwan. Now, I previously demonstrated this and made a few errors. This particular model is a 32 channel. Features I'm going to show you today are all available on the 16 channel. Now, the 16 channel entry level analyzer with protocol decoder is £174 including the VAT. So if we take a look at some of the connections, this is channel A, which is actually port A and port B, 16 channels. Then you get port C and port D on the 32 channel analyzer. These connections are specifically for the higher end faster model with more memory. You can plug in this external module to give you 200 megahertz external clock. These are the two ground pins that you have to ground this to your device. This is an external clock. You've got two options of running with this cube. You can have it synchronize on its internal reference clock or synchronize to an external clock. So you've got various pins for reference in and out, and then there's the external clock. So on the 32 channel, you get 32 wires. And that's the length of them. On the 16 channel, you get, I think it's 2 lots of 8. And you get the regular USB lead that plugs in the side here. So PC based, PC or laptop, and they work with Windows 10. Now, one of the errors I made, all the models are supplied with all these probes, with the exception of the entry level. So on the entry level, 16 channel, 32 kilobit memory depth, you get the analyzer, 8-pin testing cable times 2, but then look, probe 2. Oh, hang on. So you get 16 wires for 16 channels, but only 2 probes. So I seriously do not know why they're shortchanging the entry-level buyers on these probes. How you're meant to connect the other 14 leads, plus the earth, plus the external clock if you want to use it. So as I've mentioned previously, installation DVD, nice camera case. What I'll do, I'll put on screen now a list of the 121 protocols that the LAP-C series decodes. So whilst we're looking at the cube itself, this button here is a capture button. When it's connected to your device under test, you simply press that button. It will sit there waiting for the leading edge to come in. Right, what I'll do is connect this logic cube up to this clicker 2 board. Now via UART, this board is sending GPS time, pressure, humidity and temperature, and also the battery voltage. So this microcontroller sends a message requesting the data, and then via this H2C and Bluetooth, it sends the data back. Right, here's a quick look at the capture window. Now this is looking at all the data. There's the trigger point. There's the timing in milliseconds. So if we zoom in, these 2 buttons here, zoom in here, and you get a navigation window down the bottom here. Just follow the mouse. So you can see I can look at this bit of data here, or this bit of data here. So concentrate on this first bit of data. Zoom in. So this yellow waveform here, this is the UART. So we've just got 1 wire, asynchronous, no clock pulse. Now this ZeroPlus Logic Cube decodes this serial data and gives us our decoded data up here. So if we change this to ASCII so we can understand it, so we right click, numeric base encoding, ASCII. So if I zoom out a bit, this is the first message my Fusion board sends to that mobile board. So $, turn on GPS. So if I zoom in, so being UART, go to the beginning. These are like start bits in blue and stop bits in red. So that's the data, decoded as a T, then a U. So you can zoom in and analyze the waveform against the data and the start and stop bits and learn how the UART works. Now in this particular case I'm using the standard UART, but if we right click on this UART, bus properties, I'd already selected UART, and you can go configure here, and by default without adjusting anything, so non-parity, one stop bit, least significant byte, then the most significant byte, data length, percentage sample, and then the baud rate. And these are the colors, you can change them. Colors are the start, stop bits, parity bits. So if I want to zoom back out, look at all of the data, click up here on this blue box, show all data, F10. That's the first bit of data we've just looked at. Now I can move this navigation window, or just simply move this across to the next bit. Now I can zoom in down here. So if I zoom out and look at this blue box around the navigation window, I can simply move to the next bit of data. Now this is quite important. So we had a bit of data here, and many milliseconds later we had this bit of data. So if we were capturing all this in memory, this gap in the middle is wasted. So there's a button up the top here. You can compress this space. Looks like it's that one there. Compression. You can tell the cube to compress the data. It enables you to capture up to 255 packets. This first box, you can get the device to trigger on the first count, depending on your trigger point here. So this is high, low, going from low to high and high to low, and that's either, and blank is it doesn't matter, it will trigger on anything. So you can tell it to trigger on, say for example, the 5th edge. This trigger page, I believe you can count up to 255 packets of information. This box here, the height, that's setting the waveform to 50. You can make it larger or smaller. This 50% is if you want to capture some edges in front of the trigger point. You would set this to say 50-50, so you get 50% ahead and 50% after the trigger point. So in this example, everything is after the trigger point and we had nothing before. Or you can set that down to 0, so nothing in front of the trigger point is captured. This is the internal clock. And as a rule of thumb, you sample your device under test should be sampled at 4 times the frequency of the device you want to measure. So in this case, we're looking at 9,600 baud rate. So yeah, roughly 4 times faster, 50 kilohertz will do. Now this is using the internal clock. So this is asynchronous. These edges aren't synchronized to the device under test. They're synchronized to the internal clock. So this capture is evenly spaced with reference to the internal clock. If you select external clock, these bits of data will be linked to the external clock. This 64K, so on the standard entry level, say £174 with VAT, 32 kilobits per channel, and you do have the option of doubling it, but then you lose your ability to compress the data. So this is the trigger, that's the start, that's the data. These bars are like cursors, they call them bars in this software. You can move them along, and looking at the data just up here, you can measure the distance from the trigger to an edge, or from an edge to another edge. So if we go over here, for example, the distance from A to B, up here, A to B, 3.14 kilohertz. For A to the trigger, that's the frequency. You can also click on this little window here I'll give you the timing. So that's a brief rundown of this when I've already captured the data. And of course, the advantage with this software, we can save this waveform and save the data. So go save as, and it'll save that data so you can look at it later. Or you might have just seen screen capture. So we can save this whole screen and print preview, export. So you can export the packet list. So that's one thing I haven't shown you yet. Let me go view, packet list. That's down here. If I move this up, we can. This is the data in hexadecimal format. So it's been decoded into ASCII up here. They're the hexadecimal characters for those letters. We can export this packet, export it and save it onto a PC or export it somewhere else. So I've used the internal clock to capture this data, but if we come over to here, right click, acquisition setup. So this is the default, and you can see I've adjusted the clock to 50 kilohertz, internal clock, or we can use an external clock and tell it, do we want it to synchronize on the rising edge or falling edge? And that's the sample memory depth we're using. So 32 kilobits per channel. So we've got 75 meg bandwidth, up to 100 megahertz internal clock on most of the units. What I'll do now, I'll clear all this, delete all channels. To restore all those channels, you can just go restore defaults. But so I will now set up that UART to capture the data from that remote module. So I want just one channel. Channel assignment. So this is, it starts at port A, B, C and D. On the 32 channel, if you want to upgrade the memory from 2 megabits per channel to 4 megabits per channel, you lose the additional 16 channels. So here we're just going to add bus, port A, channel 0. You can name them here. So UART 1, go OK. So UART 1, group into bus. The color will be yellow. And I can now either press the button on the cube and wait for it to trigger, or press this single capture up here. This is repeat capture, this is single capture. Right, my data's about to come in, so hit the trigger point here. I want a transition from low to rising edge. Hit the single capture. Although it says filling buffer, it's not filled until it sees the capture edge. Now I've had to restart this, so if I quickly stop it before my data comes in, so 32K, 50 kilohertz, 0% there, right, ready, capture. So we can change the colors here by a double click. Yellow for the waveform, green is the decoded data. Move the cursors along. Now what I haven't done yet is told it what protocol, but that can be added after. So right click, bus properties. You can click this button here or click in this window. Find the protocol you want easily. Type in here UART. You say UA. There's just one UART. Okay. And that's decoded our data. This is the UART in yellow. Our logic level with times. Start. Data, stop, start, zoom out. Here, just move along. There's our trigger point, so we captured nothing in front, didn't waste memory on that. The data is in hexadecimal format, so we can right click, numeric base encoding, ASCII. Now currently my transmission of the temperature is corrupt. Not sure why. I'd have to use this decoder to figure it out. So if I zoom out, this has been happening all afternoon. This should say temperature, and if I zoom in a touch, there's data, stop, start, data. But if I move along, maybe it's because the battery is running out, I'm not sure. So if I zoom out, there's a temperature. So I'm getting the correct reading, just not the word at the beginning, which my fusion board needs to decode or to pick up on this signal and decode it. So at 17 degrees, and this is the next piece of data which is correct and complete. So $ humidity, 49% relative humidity. Pressure, 1010, so millibar. And finally, I said that clicker 2 was transmitting the battery voltage. So dollar voltage 3.756111. So I'm sending a float and just picking up the last two significant bits here after the decimal place. So back up here, zoom out, look at all the data, show all data, F10. From that, blue marks are DP and DS under the trigger. That's the total memory there, using the 30s UK memory depth. So that's a quick look on how to capture a single bus and decode it as far as UART goes. Easy to set up once you know how, and quite intuitive once you know you've got to group these signals into a bus if you want some sort of serial decode. So for logic analyzers and serial decoders and lots more test equipment besides, and for development boards, compilers, test equipment, displays, head on over to the debugstore.com and you'll find hundreds of more products. Hopefully you found this video useful. If you like it, don't forget to click like. Thank you very much.